All right.
To YouTube.
So, looks like we're live now. Didn't forget this time, already on better track. All right, so hello everybody. Today is mostly going to be just going over the practice quiz that you guys did and just making sure that you feel good about being able to take the quiz on Tuesday. So let's start off. Are there any specific questions that people have that we want to go over? Any specific problems that people had issues with?
Can we do 7 on the homework?
7? Sure. Let's go down there. All right. So we are negating the quantified predicate and then determining whether the original statement or its negation is true. So let's start by rewriting the statement with the negation around it. So for all x in the set integers, there exists a y in the set of integers such that x plus y equals 10. So with these negation problems, you just want to go through each section and negate that part. And we know when you negate a quantified predicate, you flip the sign and then negate whatever is to the right of it. So I'll do this first term and then I'll let you guys work on it for a second. So for this first one, we're gonna apply the negation to the very first term, which is gonna turn it into there exists an x instead of for all in the set of integers. And then we negate the rest of this. So x plus y equals 10. All right, and then you're gonna follow that same step for the other two terms until there is no more, there isn't a negation sign anywhere outside of parentheses. So go ahead and work on that for a minute. All right, I'm gonna pull you back. Does anyone want to volunteer to say the next term? So we'll rewrite this one again. There exists an x in the set of integers. So who wants to negate the next portion?
So that would turn into for all y, a part of integers set z.
All right, and then we apply the negation to the last section. Okay. And then let's rewrite the beginning. And it's always good to show your steps in these because at least then if you end up making a mistake somewhere along the way, you can still get credit for the portions that you did correctly. So for this last one, what is the negation of x plus y equals 10?
Is x plus y is not equal to 10.
Awesome. X plus y is not equal to 10. Okay, so the second part of this problem is figuring out if the original statement or the negation is true. So are there any guesses? Are there any, let's see, let me come back to Zoom. Are there any answers in the chat? Okay, so the original is true. And this one is a little bit tricky because at least I had a second where I forgot. So integers do include negative numbers, which means that for every x, for every integer x, there is going to be another integer that you can add to make 10. And there's no counterexample that you can find that will prove that. That won't be true. But the negation says that there is an x such that for every integer y, adding them does not equal 10. So we know that that's not true because if you take any integer in the set of integers and try to find something that won't make it equal to 10, you won't be able to find that. Are there any questions on that?
So when you're writing your answer to which one is true, should you provide a counterexample to show why it's
You don't
true?
need to specify a counterexample unless there is one that it specifically asks for. So in this case, you can just say the original statement is true.
Okay.
All right. Anybody else have a practice quiz problem we want to try?
Could we do a homework problem?
Yeah, sure. Which homework problem?
Number 7.
Number 7. Let me go. Let's see. All right. So this is another one of those negation problems. And what helps me a lot when I'm trying to find the negation of an English sentence is to switch it into logic first. And sometimes we might ask you to do that, but sometimes it's just good to do that even if we don't ask you. So let's start by writing this one in symbolic logic. So let's start just section by section. First one says for every positive integer x. So for every translates to for all. So for all x in the set of positive integers, and you can write that with just the integer symbol and a plus. And then we see there is a positive integer y. So there is translates to there exists. So we've got there exists a y in the set of positive integers. And such that just usually is just a comma. So we don't need to write that in any specific way. Y is smaller than x. Actually, let's just start with y is smaller than x. So that one is something we're more used to. Y is less than x. And then we have an and, which indicates that we need to use symbolic logic. So the and symbol, and y is a factor of x. So there were a lot of questions on this one on Piazza. There are a lot of ways to write that y is a factor of x, and any of those would be totally fine to put. So one is that, let's see, y is a factor of x means that y, oh boy, I always get these mixed up. I believe it's y equals xk. Oh gosh. X times k. Is that right?
I thought it was x equal to y times k.
That might be, I always get mixed up on these ones. This is a good thing to put on your note card as well, because remembering exactly is kind of difficult because there is y divides x. Is that, oh my goodness. I'm having like a total brain fart. 1 second.
I think should be x equals to y times k.
Okay, so x equals to y times k. And let me go up to see. Okay, found it. So there's also, let's see. We can also say that y divides x. That's also valid. And we also have, there was one person who said you could put, let's see, I think x over y equals k. And with both of these two, it's probably good to specify that k is also in the set of integers. But any of these three are totally acceptable to say that y is a factor of x. And it doesn't matter too much about the notation of how to negate that, because for this problem, we're writing it as an English sentence anyways. So I'm just gonna stick with y divides x, because that's the easiest one to remember for me. And then let's go ahead and negate it. Okay, so for the negation on this one, I'll let you guys work on this one again since it's really similar to the last one, and then we'll go through the answer together.
So you can write down y is a factor of x in that way?
Yeah, you could do it for this problem. The main goal here is just to understand what the English sentence is saying so that it's a little bit easier to negate it. But yeah, since you're translating it to English later, you don't need to write any specific symbol for y is a factor of x, or y is not a factor of x. All right, I'm gonna bring us all back and let's go through the negation in logic, and then we'll translate it to English. So the negation of the first part is going to be there exists an x in the set of positive integers, and then we negate the rest. All right, and then we go on to the next section, copy down what we already took care of. And we see that for all y in a set of positive integers, we have the negation of this part. All right, now this last part is a little bit tricky because we need to use Demorgans to negate it. So I'll copy down what we've already got, and then does anyone volunteer what they put down?
It's y greater than or equal to x, or y is a factor of x.
So it'd be y is not a factor of x, which I'll just leave as just not y divides x, which if we were doing this in a problem that said make sure you get it all the way down, we wouldn't want to leave that. But like I said, there's not really a symbol that says y is not a factor of x. So since we're translating this to English, it's okay to leave it like that. But yeah, so you just negate both parts of, you negate either side of the section and then flip the symbol. So translating this, we kind of did it into English while we were going through it, but we'll just write it out anyway. So we have there
Exists.
A positive integer x such that,
Wouldn't it be for every positive integer y?
for every positive integer y, y is greater than x, or y is not a factor of x. Okay, everyone see how we got that?
For y is greater than or equal to x, would you put y is at least the value of x?
Yeah, you could do that as well. And I actually forgot greater than or equal to. Whoops. I'm just gonna move all of this over. Yeah, so for is greater than or equal to, we could also have at least. That would be another option. And I think we went over this in the last discussion as well. When you're translating it into English, there are a lot of different ways to do it. So most of those are going to work as long as it's the same. So like you could say there exists an x in the set of positive integers. You could say there is a positive integer x. Any of those kinds of like common phrases that we use to translate to notation, you can use when you're translating to English as well. Any other questions on that one? All right. So I'm gonna go back to our quiz questions. Were there any more practice quiz ones that we want to go through?
I have a question about the homework. It's just like the question 2. It is possible to do it?
Yeah, sure. Oh, where did we go? There we go. And then After this one, I don't think we're going to be able to do any more homework problems. So just putting that out there. We're going to focus on the quiz after this, if that's okay. Okay. So, let's see. So this one involves, let's start with just getting the first 5 terms. And then there are a couple ways to get the recursive formula. So we'll go through both of those as well. So to write out the first 5 terms of the sequence is pretty straightforward. We just plug each number into the n. So for A1, we have A is 2 to the 2 times 1 minus 1 minus 1, which is going to be 2 minus 1, which is 1. And then we'll follow that same pattern for 2 through 5. And I will give you guys, let's say, 3 minutes for everyone to work on that. All right, it's been about 3 minutes. So I don't want to spend too much time on just plugging in. So I'm just going to let people shout out what they got for these answers. And then if you got confused on how they came to be, we'll stop on that one and go through it. Sounds good? So for A2, does anyone want to volunteer for what they got?
7.
Okay. A3,
31.
A4,
127.
And a 5.
511.
Okay, awesome. Is anybody confused on how we got those numbers? Okay, so we'll just go ahead and head on. So the way that I like to do the recursive formula is to just kind of like figure out the patterns in the sequence. And that can sometimes be difficult depending on the sequence, but for this one, what I noticed right off the bat, I like to go through and notice the difference between each number. So between this, we've got 6, and then 31 minus 7, we've got 24. 127 minus 31, we've got 96. And 511 minus 127 is 384. So what I notice here is that all of these changes in between the numbers, they're going up by 4 or 4 times. So like 24 is 4 times 6, 96 is 4 times 24. So that is a good hint. Let's see, let's start by writing A1 equals 1. That's always a good step. But yeah, noticing those changes usually indicates that we've got a scale of 4. So 4a n minus 1. But we're still missing something, because if we plug that in, then we just have 1 times 4 is just going to be 4. And we know that that's not A2. But in this case, we are only 3 away from 7. So let's try adding 3 and see if that works a little bit better. So we know that it works for A2, but let's double check for A3. We get 4 times 7 plus 3, which is 28, plus 3, which is 31. And if you go through the rest of them, you'll see that it's the same pattern. And then the other way to do it is to use algebra. We've seen a couple examples of this to just rigorously derive it. So we know we are given that an equals 2 to the 2n minus 1 minus 1. And we can just plug in n minus 1 for n. So we get n minus 1 equals 2 to the 2, and then instead of n, we plug in the whole n minus 1 minus 1 minus 1. All right, so let's go through and simplify this. We have 2 to the 2n minus 2 minus 1 minus 1. So an minus 1 equals 2 to the 2n minus 3 minus 1. And then this is a good place where it's important to know your algebra pretty well. I'm just going to move this down. Because this can be rewritten to be 2 to the 2n over 2 to the 3. Does everybody understand how that worked out? So an minus 1 is equal to, actually, let's see. Yeah, is equal to 2 to the 2n over 2 to the 3 minus 1. Right. So now we can add 1 to both sides, and we get an minus 1 plus 1 is equal to 2 to the 2n over 2 to the 3, and this 1 gets eliminated when we add 1. And then we can multiply by this 2 to the 3rd, on both sides, which is going to give us 8a to the n minus 1 plus 1 equals 2 to the 2n. So that gives us 8a n minus 1 plus 8 equals 2 to the 2n. Right. Oh my goodness. Nancy?
Are you trying to use the recursive one to get the closed one, or?
The closed one to get the recursive.
Oh, okay. Isn't that already the recursive one? The an equals to 4 times an minus 1 plus 3?
Yeah, I was trying to show the way that you can derive it through algebra because I know a lot of people have struggled with just coming up with the recursive formula without that. But it is possible that that is not an option on this one.
Okay, so you're trying to plug in the an minus 1.
Yes,
Okay.
which usually works itself out, but I think I must have done something wrong.
I think you can pull out the,
I'm like, we're so close.
I think you, instead of taking out 2 to the 3, you can take out like 2 to the 2, and then it's just 2n minus 1, which matches the an.
Yes, thank you. Sorry about that. Oh my goodness. So these ones definitely take practice. So let's go ahead. All right. So 2 to the 2n minus 1 over 2 squared minus 1, I think. And then we can still do the, can we multiply on either side? Oh, add the 1 first. That's what I'm missing. An minus 1 plus 1 equals 2 to the 2n minus 1 over 2 squared, which is going to be 4an minus 1 plus 1 equals 2 to the 2n minus 1. So 4an minus 1. I might have to work on this one and get back to you guys. I'm going to keep trying to figure this out the other way, and then I will try and post that solution right after we finish this discussion so that you can go back and look at it later. Sorry about that. I know that
It's
do it, but
just 4, so it starts at 0 instead of 1, because it's usually 4 times the previous plus 3.
yeah. Sorry, what were you saying?
Well, the
I think
recursive,
you just have to
sorry, go on.
No, I was just gonna say, I think you just subtract both sides by 1, and then you'll get the right answer.
Yes,
Because
thank you. Oh my goodness, everybody, I'm so sorry. So if we subtract, there we go. I knew that we were close. So that's 4an minus 1 plus 3 equals 2 to the 2n minus 1 minus 1. And we already know that 2 to the 2n minus 1 is a to the n. So we can substitute it back in. Thank you, Kevin. All right, we got there. That's 2 different ways to get the recursive solution. So hopefully that's a little bit more clear. I know we got a little bit lost in the weeds there, but made it out on the other side. Does anyone have any questions on that process? Okay, so I'm going to go back to our discussion and focus on the quiz questions for the last few minutes. We've got about 15 left. And just, there are also, if you feel good about the practice quiz, there are a few more questions. We've got proof by cases, logic, implications. I think we won't do another predicates today because we did a couple of them already. But we do have a few different topics at the bottom if there's anything that you want a little bit more practice on.
We could do the proof by cases first and then see if we have any time left.
Was it up here? Proof by cases. Yes. Okay. So this one is really probably a little bit more tricky proof by cases, but it is a good practice. So the hardest part of this one is just figuring out what the cases are going to be. Because we've got that if n is any integer not divisible by 5, then n has a square that is of either the form 5k plus 1 or 5k plus 4. So let's first just figure out, we've got our hypothesis, which is if n is any integer that is not divisible by 5. And we were talking about earlier that there are a few different ways to write this. But I'm going to say that this means that n mod 5 does not equal 0. So what is, I'm trying to think of how to explain this. The 4 cases, we're trying to account for every case where n is not divisible by 5, because there's lots of numbers that are not divisible by 5, and it's kind of hard to sort them. So does anyone have any guesses what is one way we could separate this into cases? Okay, so it's a little bit different because we're used to doing n is even, n is odd, and those are maybe things that we're more comfortable with. But for this one, if n mod 5 is not equal to 0, then it has to be either 1, 2, 3, or 4. And it can't be 5 because n mod 5 is never going to be 5. That's just basically 0. So these are our 4 cases we have if the remainder is 1, 2, 3, or 4. So I will do the first one with you guys, and then I will let you all try the last 3 cases, and we'll check in after every single one of those. Sounds good? Okay. So for the first case, we've got that n mod 5 is equal to 1, which basically means that n is equal to 5 times some integer, let's call it j, plus 1. And then we have to specify that j is an integer. Does that make sense how we moved it from the mod to the division notation? Okay. So now we need to, let's see, the next part is that n has a square that is of one of these 2 forms, which gives us a clue that we need to square this. And we can just do that by substitution. Squared. Multiplying that out gives us 25j plus 10j plus 1. And then we can do factoring, pull out the 5, and that gives us 5j plus, or whoops, this is supposed to be j squared, plus 2j plus 1. And then we can simplify this section because of closure. So we just have to make sure to specify n equals 5k plus 1, where 5, whoops, not 5, where k is an integer by closure under addition and multiplication. And on a formal proof, it's good to have like descriptions of why you're going through all of these. So I would probably be more specific if I was doing a formal proof where I'd specify factoring yields this line, substitution yields this line, you know, stuff like that, to just make sure that every single thought process, every single step that you're taking has a reason and it's not just arbitrary. So for number 2, I'll get it started. You've got that n mod 5 equals 2. And remember that in cases, you can reuse the same variables because they are technically independent proofs. So we can again write n equals 5j plus 2, where j is in the set of integers. So I will give you, running out of time, so I'm going to give you 2 minutes to get started on that. It's okay if you don't finish, but just get as far as you can. All right, that's 2 minutes. So let's get started on the second case. Nice thing about proof by cases is once you've done the first one, usually the rest are pretty similar. So what is going to be the next step?
N squared equals the whole thing squared and then factor it out.
5j plus 2 squared. All right, and multiplied out is 25j plus j squared plus 20j plus 4. And then we can factor out the 5 again and get 5j squared plus 4j plus 4. And what's next?
Closure.
So by closure, we know that this is 5k plus 4, where k is in the set of integers, again by closure under addition and multiplication. And we already know, I meant to say this last time, but we're double checking that they're in the form of 5k plus 1 or 5k plus 4. So far, we're good. So let's just do 3 and 4 together really quick before we run out of time, and then I'll take questions. So for 3, we have that n mod 5 equals 3, which essentially means that n equals 5j plus 3, where j is in the set of integers, and we can square both sides. Oops. Which gives us 25j plus, I believe it's going to be 30j plus, no, that's not. 5. I think, yeah, 30j plus 9. Okay, yeah, that was right. Okay. And let's see. So n squared is going to equal 5. Oh, okay. So this one we have to kind of split up. Plus 30j. If we do plus 5 plus 4, that is going to equal the same thing as plus 9, but that gives us something to factor out. So now we can factor out of 5 and get 5j squared plus 6j plus 1 plus 4. And that allows us to use closure to get 5k plus 4, where k is in the set of integers. That one's a little bit trickier, but sometimes you just have to manipulate the numbers to get the result that you're looking for. And then let's do this last one, which is that n mod 5 equals 4. And that gives us n equals 5j plus 4, where j is an integer. Square both sides. I'm not going to forget the j squared this time. So we get 25j squared plus 40j plus 16. And again, we have to do a little bit of manipulation here. But if we take 25j squared plus 40j plus, does anyone know what we can split this one into?
Plus 3 on the so it'd be 5 times 5j squared plus 8j plus 3.
Plus 8j. So what we're looking for right now is for it to be 5k plus 1 or 5k plus 4. So we want to have either a 1 or a 4.
Oh, I was saying plus 3 in the factoring out, and then it'd be a plus 1 outside of the parentheses, if that makes sense.
Gotcha. Okay. Just a little ahead of the game. So yeah, we will end up with 3 in the parentheses, which means we're going to do 15 plus 1. And that lets us factor out the 5 to get 5j squared plus 8j plus 3 plus 1. And again, we can use closure, and that gives us 5k plus 1, such that k is an integer. And then we're not quite done, because before you finish, it's always good to summarize and say something like, since all cases are true, the proposition must be true. And then you can do QED, or I've always just seen a box. That's how I always finished a proof. Okay, we kind of went through that a little bit quick and we're out of time, but are there any quick questions before I let you all go?
How do you know that you just had to like check for 1 through 4 in your cases?
So that one's a little bit tricky. You'll get used to it more as you do more of these proofs, but basically we're assuming that the hypothesis is true, and then we're making sure that the prediction is true. So our hypothesis is that n is any integer not divisible by 5. So in order for n to not be divisible by 5, then dividing by 5 is going to leave some remainder, and the remainder is either going to be 1, 2, 3, or 4. Does that make a little bit more sense?
Yeah, I think so.
All right, any other questions? All right, if that's all, then I will see you guys next week, and good luck on the quiz, and have a great day.
Wait, when are the review sessions?
That is a good question. Mine is going to be from 10 to 11 tomorrow morning, but let me double check on the rest of them.
I think James gonna hold his soft sour on Monday.
Hmm?
Is it James gonna hold his soft sour on Monday?
Yeah, I'm not sure what time it is though. I think it might be 3 to 5. I'm just double checking right now. Where did I write that down? Okay, there we go. It should be in this slide. Okay, so mine are from 10 to 12 tomorrow. And then Mark is doing a review from 1 to 3 tomorrow. And Ilkin is going from 3 to 5. And then on Monday, James is going to have his from 3 to 5 as well.
Okay.
So most of them are tomorrow, and then there's one on Monday.
Thanks.
Yeah.
Thank you.